A black hole could become our greatest engine. This is the promise of the halo drive, a concept where we don't build a rocket, but commandeer the most powerful forces in the cosmos. By the end of this exploration, you will understand how a dance between two black holes might one day fling our descendants to the stars. We will uncover how light can be turned into a cosmic slingshot, and why this idea rests on a knife's edge between genius and impossibility. What does it truly mean for humanity to reach for a galaxy? The secret to escaping our solar system was discovered not with a bigger rocket, but with a cosmic trick. For decades, our most distant spacecraft have used a simple principle to steal speed from the universe itself. It is called a gravity assist, and it works like a perfectly timed push on a cosmic swing. A probe approaches a planet from behind, falling into its gravitational pull. As it swings around, the planet's immense motion through space acts like a slingshot, hurling the probe onward with significantly more velocity than it arrived with. The planet pays for this boost with an imperceptibly tiny slowdown, a trade made possible by the unbreakable laws of physics. This technique powered the Voyager missions on their grand tours, using the gentle tugs of Jupiter and Saturn. Yet for all its elegance, a planetary gravity assist is a whisper of what is possible. A planet's gravity is a gentle hill in the fabric of space. A black hole, by contrast, is a bottomless well. Approaching such an object, the energy you could theoretically gain is not just greater, it is transformative. We are talking about boosts that could accelerate a ship to a meaningful fraction of light speed, turning a journey of millennia into one of centuries. But here lies the first great challenge. To use a black hole for a gravity assist, your trajectory must be flawless. Come too close, and you cross the event horizon, a point of no return from which not even light can escape. Stay too far, and the boost becomes negligible. You must skim along a razor's edge, a precise path where gravity is strong enough to whip you around, but not strong enough to capture you forever. It is a maneuver of breathtaking precision, a dance along the edge of oblivion for the promise of unimaginable speed. This daring concept sets the stage, but it is merely the prelude to an even more audacious idea. This is the cosmic catch-22 of a solitary black hole. Imagine you have successfully navigated that razor's edge, skimming just outside the point of no return. The black hole's gravity whips you around at a staggering fraction of light speed, a boost far beyond any chemical rocket. But then you face a new and daunting reality. You are now on the far side of the gravity well, still caught in its immense pull. To break free and continue your journey to the stars, you would have to fire your own engines, burning through colossal amounts of fuel to climb back out of that deep gravitational valley. In doing so, you would sacrifice most, if not all, of the speed you just gained. It is a heartbreaking trade, like using all your strength to climb a mountain only to slide back down the other side. The single black hole gives a phenomenal push, but it also holds on, demanding a costly payment for your release. This fundamental flaw means a lone black hole, for all its power, is ultimately a dead end for a practical star drive. We need a system that not only accelerates us but also elegantly lets us go. This requirement shifts our gaze from a solitary titan to a pair of them, locked in a mutual orbit. The solution emerges not from stillness but from motion. It lies in the chaotic, beautiful dance of a binary black hole system. Two colossal shadows circle one another in a silent, eternal waltz. This is the binary black hole system, and within its chaotic grace lies the solution to our propulsion paradox. Instead of a single, static gravity well, we now have two immense masses in motion. Each black hole warps the fabric of space-time around it, but as they orbit, those individual warps combine and interact, creating a swirling, dynamic vortex. It is like a whirlpool that itself is moving through the ocean. This motion is everything. A spacecraft approaching this system isn't just dealing with the gravity of a stationary object, it is entering a landscape that is actively churning. The black holes possess enormous orbital momentum, a kind of stored kinetic energy from their endless dance. And here is the revolutionary idea, a concept known as the Penrose Process. It proposes that an object can dive into this turbulent region near a rotating black hole and emerge with more energy than it arrived with. The object essentially steals a tiny fraction of the black hole's rotational energy, causing the black hole to spin ever so slightly slower. In a binary system, this principle is supercharged. A spacecraft could use the complex gravity of the orbiting pair to execute a maneuver where it gains a tremendous boost in speed, with the cost being paid not from its own fuel tanks, but from the orbital energy of the black holes themselves. Their dance imperceptibly slows while the ship is flung away at a significant fraction of light speed. This is no longer just a gravity assist, it is a gravity theft orchestrated on a cosmic scale. But how exactly do you pull off such a heist? The answer involves not a ship, but a beam of light. Theoretical physicist Roger Penrose saw a black hole not as a dead end, but as a bank of stored power. His insight focused on a special type, a spinning black hole, where the intense rotation warps space-time into a vortex. Just outside its event horizon lies a turbulent zone called the ergosphere, where space itself is dragged around at impossible speeds. Penrose realized an object could enter this region and, through a clever maneuver, come out with more energy than it went in with. Think of it not as a box of garbage, but as a daring energy trade. If an object splits apart within the ergosphere, one fragment can be sacrificed, falling past the point of no return, while the other fragment escapes. The escaping piece carries away a portion of the black hole's immense rotational energy, leaving the cosmic giant spinning ever so slightly slower. This is the Penrose Process, a theoretical blueprint for mining the spin of a black hole itself. It transforms these objects from passive traps into potential power plants. The Halo drive takes this blueprint and refines it with a stroke of genius. Instead of sending a fragile, complex spacecraft to perform this dangerous splitting act, the drive proposes we use something far simpler and faster, light itself. A laser beam becomes our projectile. We fire it into the swirling ergosphere of one black hole in a binary pair, aiming it on a precise trajectory so that it steals rotational energy and is flung out with dramatically increased power, like a beam amplified by the universe's most powerful lens. This supercharged light would then be directed to strike a light sail on our distant spacecraft, transferring that stolen momentum and pushing the vessel to incredible speeds. We shift from a physical slingshot where the ship itself must take the risk to an optical catapult where only information and energy brave the edge of the abyss. Light becomes our cosmic emissary in this grand design. The Halo drive sidesteps the peril of sending a ship into the abyss by using a beam of pure energy to perform the heist. From a position of safety, perhaps a station orbiting a distant star, we would aim a powerful laser with impossible precision. Its target is not the ship, but the swirling ergosphere of the first black hole in the binary pair. The beam does not cross the event horizon, but instead skims along that final boundary where space and time are dragged into a frenzy. Here, gravity performs its first miracle. It bends the path of the laser light so severely that it acts like a mirror, a phenomenon known as gravitational lensing. But this is no ordinary reflection. As the light passes through this distorted space, it engages in the Penrose process, stealing a minuscule amount of the black hole's rotational energy. The laser pulse emerges not just redirected but supercharged, amplified by the raw power of spacetime itself. This energized beam then races across the void between the two titans. It approaches the second black hole, entering its own zone of extreme gravity. The process repeats, the light gaining another tremendous boost as it is lensed around the second vortex. Finally, this now immensely powerful pulse of light is carefully aimed back toward our waiting spacecraft, which is equipped with a vast, reflective light sail. When the light strikes that sail, it does not carry heat but momentum. Each photon pushes with a tiny force, and in this concentrated, amplified torrent, that force becomes colossal. The ship, having never ventured near the danger, receives a clean, smooth acceleration, pushed by light that has been twice forged in the furnaces of black holes. It is a chain reaction of cosmic proportions, where we use gravity's own distortions to create the ultimate propulsion beam. The elegance is breathtaking, but the practical hurdles are equally staggering. This precision hinges on a ghostly orbit, a path of pure light and perfect balance known as the photon sphere. Envision the event horizon as the final gate, the point of no return. Just outside it, the black hole's gravity reaches an almost impossible intensity. Here, the curvature of spacetime becomes so severe that it creates a celestial racetrack for light itself. This is the photon sphere, a theoretical shell where gravity bends the path of a photon into a perfect circular orbit. A beam of light entering this region at just the right angle would not escape to infinity or plunge inward immediately. Instead, it would be captured, whipping around the black hole in a precarious loop, perhaps once, twice, or even dozens of times before its fate is decided. It exists in a state of perfect instability, a cosmic tightrope walk between freedom and capture. For the halo drive, this fragile orbit is not a curiosity, it is the essential conduit. Our laser pulse must be aimed with unimaginable exactness to graze this photon sphere around the first black hole. The goal is not to trap the light forever, but to use this gravitational lensing at its most extreme. As the light streaks through this bent space, it steals that rotational energy and is then flung outward, not on a random path, but on a specific trajectory aimed directly at the second black hole in the binary pair. This is not a simple bounce, it is a calculated ricochet off the fabric of reality itself. The margin for error is vanishingly small. A targeting mistake of a fraction of a degree or a timing error of a microsecond would send the precious laser pulse spiraling into the void or down into the abyss, wasting its energy forever. It demands a navigation system that can account for the wobble of spinning black holes, the subtle drift of their orbits, and the chaotic warping of space between them. We are talking about aiming a beam of light across light years to hit a moving target the size of a solar system, and then having it strike a zone only marginally larger. Our current mastery of deep space navigation, as impressive as it is with probes across the solar system, would be utterly inadequate for this task. It would require a leap in our understanding and control of physics that borders on the magical. Yet, if we could achieve such control, we would hold the key to the stars. This apparent energy gain feels like magic, a cosmic trick where something is pulled from nothing. Yet the universe's ledger is always balanced, and the halo drive's secret lies in its source of power. The supercharged laser pulse that pushes the spacecraft did not create energy from a vacuum. Instead, it performed a delicate act of cosmic withdrawal, siphoning a tiny, almost imperceptible amount of rotational energy from the black holes themselves. Every time the light beam grazes the ergosphere and is amplified, it leaves the black hole spinning just a fraction slower. In a binary system, this stolen spin translates directly into orbital energy. The dance of the two titans becomes ever so slightly less energetic. Over countless cycles of a halo drive in operation, this effect would accumulate. The black holes would draw closer together, their orbits decaying a tiny bit faster than they would naturally from gravitational waves alone. They are not just engines, they are fuel. The drive uses them as the ultimate cosmic battery, converting their immense, stored momentum into propulsion for our ships. we would be spending the gravitational capital of black holes to buy our ticket to the galaxy. This raises a profound and almost philosophical question about our place in the cosmos. Are we merely observers, or do we become active participants in the life cycle of the universe's most extreme objects? By using a halo drive, humanity would not just be traveling among the stars, we would be subtly altering the fate of celestial giants, hastening their final embrace in a merger that would shake the fabric of spacetime itself. The power for our greatest leap forward comes from borrowing against the future of the engines themselves. The targeting problem is a leap from theory into a universe of unforgiving physics. To fire a laser from a station orbiting our sun and have it strike a precise point near a black hole light years away is an act of precision that defies human intuition. Think of trying to hit a single coin on the surface of the moon with a beam of light, but that coin is moving in a complex dance, and the air between us is swirling with invisible turbulence. Now scale that challenge up by a factor of millions. The black hole's photon sphere, that critical racetrack for light, is our target. Missing it by even a microscopic margin in angle or timing means the entire maneuver fails. The laser would either vanish into the event horizon, offering its energy to the void, or deflect away on a useless path into the darkness. Success depends on knowing the targets with absolute certainty. We would need to map the exact mass, the precise rate of spin, and the intricate orbital dance of both black holes in the binary system. These are not static statues, they are dynamic, churning objects that warp the very space around them. Our calculations would have to account for every ripple in spacetime they create, predicting their position not just when we fire the laser, but for the years or decades it takes that light to travel across the interstellar gulf. This demands a new era of astronomical observation. We are talking about telescopes and sensors of such power they could measure the subtle wobble of an event horizon from across the galaxy. On the engineering side, the laser itself is a monumental hurdle. It must be phenomenally powerful to begin with, and it must maintain a beam so perfectly coherent and stable that it does not spread out or distort over its multi-light-year journey. Our current most powerful lasers would be like faint candles against the interstellar wind compared to what is needed. The guidance systems, the mirrors, the power sources, all would have to operate with a reliability and precision we can scarcely envision, functioning autonomously for centuries. It is engineering not on a planetary scale, but on a galactic one, where a single misaligned component 100 years into the mission could mean the difference between reaching the stars and whispering into a cosmic abyss. Even the most perfect blueprint is useless without the right materials. The halo drive requires a very specific kind of cosmic engine, a binary black hole system that meets a daunting list of criteria. First and foremost, it must be relatively close. We are not talking about a quick weekend trip. The nearest known stellar mass black hole is over 1,000 light-years away. For a civilization just beginning to reach beyond its solar system, a target within a few hundred light-years would be considered astonishingly convenient, but even that distance presents a staggering communications delay. Sending a laser pulse that takes centuries just to arrive means the entire operation must be pre-programmed with flawless, autonomous foresight. We cannot steer it in real time. We can only aim and hope our predictions hold true for longer than our recorded history. Beyond proximity, we need stability and clarity. The ideal binary pair would have a well-defined, predictable orbit. We would need to know their masses, their spins, and their exact dance pattern with an accuracy that borders on the absolute. This turns the quest for a halo drive into one of the greatest astronomical surveying missions ever conceived. Candidates might lurk in the dense hearts of ancient globular clusters, where stars and their remnants are packed tightly together, or as the lingering products of galactic mergers, where two supermassive black holes slowly spiral toward one another over eons. Our telescopes would need to observe these systems not for years, but for decades or even centuries, collecting enough data to map the subtle gravitational waves they emit and chart their future paths with certainty. Finally, the engine must be clean. Many black holes, especially supermassive ones, are surrounded by violent, swirling maelstroms of superheated gas and dust called accretion disks. These infernos glow with the energy of countless suns and would be utterly disastrous for our delicate laser pulse. Passing through such a chaotic environment, the coherent beam would be scattered, absorbed, or distorted beyond recognition, its precious energy dissipated into useless heat and light. We need a quiet, dark pair of black holes, ones that have already consumed the nearby matter in their vicinity, leaving a relatively clear space around their event horizons. This combination of proximity, stability, and cleanliness is extraordinarily rare. It means that before we could even dream of building the drive, we must first embark on a cosmic treasure hunt, scanning the galaxy for the perfect pair of dark engines waiting in the void. The vessel that rides this beam of stolen starlight would be unlike any ship we have ever built. Its design rejects the very core of traditional rocketry, the idea that you must carry your power with you in volatile chemical tanks or complex reactors. Instead, this craft is built for one purpose: to catch a wave. Its most defining feature would be a sail, but one of almost unimaginable scale and delicacy. Picture a sheet of material thinner than a soap bubble, yet spanning hundreds of kilometers across, perhaps even thousands. It would likely be constructed from advanced metamaterials, engineered atom by atom to be both incredibly lightweight and phenomenally reflective. This is not a cloth to catch the solar wind, it is a mirror designed to intercept a torrent of pure momentum. When the amplified laser pulse, having been forged around two black holes, finally reaches the ship after its long journey, it would strike this vast sail. The impact would not be a gentle push, but an immense, smooth, and constant force. Each photon in that concentrated beam would bounce off the reflective surface, transferring a tiny bit of its momentum to the craft. In the collective fury of quintillions upon quintillions of photons, that force becomes colossal. The sail must be engineered to withstand this without warping, tearing, or worse, vaporizing into a cloud of plasma. It is a structure that must balance the strength to handle acceleration that could reach a substantial fraction of light speed with the fragility needed to keep its mass almost negligible. The rest of the spacecraft huddles at the center of this great mirror, a tiny technological seed clinging to a colossal petal. Its structure is minimal, a protective cocoon for the essential systems, navigation sensors of unbelievable precision to keep it aligned with the distant beam, communication arrays to whisper data back home across the light years, and of course the precious payload it carries. This could be autonomous probes, dormant human colonists in suspended animation, or perhaps just the encoded knowledge of an entire civilization. There are no roaring engines here, only the silent, relentless pressure of light. Once the beam engages, the acceleration would be continuous and potentially sustained for years. The ship would steadily gain velocity, climbing out of the gravity well of its home system on this river of photons until it reaches its cruise speed. Then the beam would shut off, the sail might be reconfigured or even jettisoned, and the craft would simply coast, a silent bullet gliding through the interstellar dark at a pace that bends time itself, carrying its cargo toward a pinpoint of light that is another sun. This radical shift from carrying energy to catching it redefines the very soul of a starship. It becomes less a vehicle and more a message in a bottle, hurled across the ocean of space by the most powerful slingshot the universe can provide. But to truly grasp the scale of this ambition, we must place it beside the engines we already understand. Our journey to the stars has always been a battle against a simple, brutal equation. Chemical rockets, the workhorses that lifted us from Earth, are utterly defeated by the interstellar void. They work by throwing mass backward to push forward, but the fuel needed to reach even a fraction of light speed would outweigh entire planets. It is a self-defeating pyramid scheme of propulsion. More advanced concepts offer a glimmer of hope. Nuclear, thermal, or fusion drives could provide far greater efficiency, using the immense energy locked inside atoms to heat a propellant and blast it out at tremendous speeds. Yet even these marvels face the same core limitation. The ship must still carry its reaction mass, the stuff it throws backward to move forward. You are essentially bringing both your fuel and your exhaust with you, and the sheer tonnage required for a decades-long journey remains a colossal, perhaps insurmountable, obstacle. This is where the paradigm truly shifts toward concepts that leave the fuel behind. Imagine a vast, delicate sail catching not the wind, but the gentle pressure of sunlight. This is the principle behind light sails, and projects like Breakthrough Starship aim to use powerful Earth-based lasers to push tiny, gram-weight probes to nearby stars. The elegance is profound. The spacecraft carries no fuel at all. Its propulsion comes entirely from the momentum of light particles striking its reflective surface. But this approach has its own profound constraints. The power of the laser diminishes with distance, its beam spreading out and weakening. Pushing anything larger than a microchip to relativistic speeds would require a laser of such staggering, planetary-scale power that it becomes its own kind of impossibility. The sail, too, must be phenomenally close to perfect, and the acceleration phase is limited to the brief window before the beam becomes too diffuse to be effective. The halo drive inhabits a different category entirely. It shares the light sail's core virtue. The spacecraft carries no reaction mass, but it solves the power problem in the most audacious way possible by outsourcing it to the universe itself. Instead of a laser built by humanity, limited by our energy grids and engineering, it uses a binary black hole system as its natural amplifier. This is not just a bigger engine, it is a different kind of engine altogether. The black holes provide a gravitational lens of unimaginable power, focusing and supercharging the initial laser pulse not just once, but twice. The resulting beam that strikes the sail does not weaken with distance from its source, because its source is not a stationary laser on a planet, but the dynamic curvature of spacetime around two cosmic titans. This means the potential final velocity of a halo-drive spacecraft is not capped by our ability to generate energy, but by the fundamental physics of the black holes themselves. We are tapping into a bank of gravitational energy that has been accumulating since the dawn of the universe. It represents a qualitative leap, moving from building our own fires to learning how to steer the lightning. But this incredible speed comes with a profound and inescapable consequence, one that reshapes the very nature of the journey itself. As the spacecraft, pushed by that amplified light, climbs to a significant fraction of light speed, it enters a domain ruled by Einstein's special relativity. Here, the universe enforces a strange and beautiful rule: the faster you move through space, the slower you move through time. This is not a mechanical defect or an illusion. It is a fundamental feature of reality called time dilation. For the crew aboard the vessel, time would pass normally. They would eat, sleep, work, and age at their usual rate, but their clock and their biological rhythm would be ticking far slower than the clocks back on Earth or at the mission control that launched them. Imagine a journey to a star 100 light-years away. From the perspective of those left behind, the voyage would take at least 100 years just for the light of the ship's arrival to reach home. But for the crew traveling at perhaps 90% of light speed, the subjective trip might only feel like a few decades. They could arrive at their destination, explore for years, and begin the return journey, all within a single human lifetime aboard the ship. Yet when they finally returned to the solar system, they would step out into a world where centuries had passed. Everyone they ever knew, the entire culture they left, would be gone, transformed into history. The halo drive, therefore, does not merely change the destination on a map. It fundamentally alters the timeline of exploration. This creates staggering implications for every aspect of a mission. Communication becomes an exercise in archaeology. A question sent from Earth would take decades to reach the ship, and the reply would take decades to return. Each exchange would be a message sent to ancestors or to descendants. Mission planning cannot be adjusted in real time. It must be entirely autonomous, with the ship's intelligence capable of handling crises and making discoveries without any input from home for generations. The very purpose of exploration transforms. This is not about sending scouts who will report back within a leader's lifetime. It is about dispatching a seed, a branch of humanity that will necessarily become its own independent entity, shaped by its journey and destined to forge a future unmoored from the world that created it. The drive grants us the stars, but in doing so, it asks a poignant price. The travelers can never truly come home. They voyage not just across space, but forward in time, leaving their own era behind forever. The ship's brain must now solve a cosmic puzzle in real time. At relativistic speeds, even the smallest course correction becomes a monumental task. Think of trying to nudge a supertanker with a canoe paddle. The spacecraft, carrying the momentum of a significant fraction of light speed, possesses colossal inertia. To alter its trajectory by even a single degree would require an energy output comparable to a small nuclear detonation, applied with the precision of a watchmaker. This rules out any notion of traditional thrusters or reaction-controlled jets. The correction system itself would need to be revolutionary, perhaps using focused segments of the same amplified light beam that propels the ship, or manipulating magnetic fields to interact with the sparse interstellar medium. But the energy requirement is only the first obstacle. The universe itself begins to warp before the ship's sensors. As the vessel races forward, the starlight from ahead is compressed, blue-shifted into a blistering cone of high-energy radiation. What was once the gentle pinpricks of constellations is now a focused, hostile glare of ultraviolet and X-rays, washing out the familiar patterns of the sky. Meanwhile, the stars behind stretch and dim, their light redshifted into near invisibility. The comforting celestial map that guided sailors for millennia is utterly scrambled. A traditional telescope pointed forward would see not a navigational aid, but a blinding, featureless fog of energetic light. To know where it is, the ship's navigation computer cannot rely on preloaded star charts. Instead, it must become an interpreter of a distorted reality. It would need to take this chaotic, blue-shifted view and, using the known laws of relativity, computationally reverse engineer it back into a recognizable sky. It must ask, if I am moving at this speed, in this direction, what would the constellation Orion look like right now? Then it must compare that prediction to the scrambled sensor data in a continuous, real-time loop. This is a task of such immense complexity that it demands an artificial intelligence of profound capability, an autonomous pilot that understands relativistic optics as intuitively as we understand perspective. The spacecraft's mind must be as advanced as its light sail, a synthetic consciousness capable of making life or death navigational decisions alone, for it will be traveling far too fast to ask for help from a home it left centuries behind. Even after outsourcing its power to black holes, the Halo drive still demands a colossal down payment from us. The initial laser pulse, the seed from which the cosmic amplification grows, cannot be a mere flashlight. It must be a beam of staggering coherence and raw power, a perfectly disciplined spear of light capable of crossing light years without blurring into uselessness. To understand the scale, consider our most powerful lasers today. The National Ignition Facility can, for a fleeting instant, concentrate enormous energy onto a tiny target, but its beam is not designed for distance. It is a hammer, not an arrow. The laser for a halo drive must be the ultimate arrow, one that maintains its needle-thin focus across a void so vast our entire solar system would be a speck within it. This is not just about wattage, it is about precision on an astronomical scale. Any spreading, any diffusion, and the beam would miss the critical photon sphere by a margin of solar systems, rendering the entire intricate chain reaction impossible. The energy required to create and sustain such a perfect, far-reaching beam pushes the project from the realm of engineering into the domain of mega-engineering. We are no longer talking about building a ship or a space station. We are talking about restructuring our entire relationship with energy. To power this laser, we might need to envision orbital arrays of solar collectors so vast they could shade continents, soaking up the sun's output not for a city, but for a civilization. Or perhaps we would need to take a more profound step, constructing a partial Dyson swarm, a constellation of energy-harvesting platforms encircling our star to capture a meaningful fraction of its total luminous power. This preliminary step, just to create the starter beam, becomes a centuries-long project that would define a planetary culture. It transforms the halo drive from a single vehicle into the apex achievement of a type of civilization that has learned to weave the fabric of its solar system into a single, purposeful instrument. Before we can borrow power from black holes, we must first learn to fully harness our own sun. This immense distance creates a fundamental barrier far greater than mere space. Even traveling at the ultimate speed limit of the universe, a command sent from Earth to a halo drive system 1,000 light-years away would be a message for the distant future. The signal itself would take 1,000 years just to arrive. By the time our instruction reached its destination, the civilization that sent it would have transformed beyond recognition. This is the profound tyranny of light-speed latency, and it shatters any notion of direct control. Imagine trying to pilot a drone where every single joystick movement takes 20 centuries to register. The entire breathtakingly precise maneuver, from the initial laser firing to the final sail alignment, cannot be steered. It must be preordained. Every variable, every potential fluctuation in the black hole's orbits, every microscopic piece of interstellar dust that might scatter the beam, must be anticipated and accounted for in a master plan written centuries before the event. There is no mission control for this journey, only a set of instructions carved into the memory of an autonomous system and cast into the void. This transforms the nature of the mission from a controlled experiment into an act of profound faith in foresight and machinery. We are not launching a probe, we are launching a prophecy. A prediction of cosmic conditions so accurate it must hold true for longer than most human empires have lasted. The chain of events, once initiated, becomes an unstoppable clockwork mechanism ticking toward a moment of acceleration that its creators will never live to witness. This level of autonomous operation pushes the concept of artificial intelligence beyond any current benchmark. The system governing the halo drive cannot merely follow a program, it must become a custodian of the mission's intent. It needs the ability to perceive, reason, and adapt in real time to circumstances its human designers could not possibly have foreseen. A sudden flare from a passing star, an unexpected gravitational ripple from a distant galactic merger, a tiny degradation in its own sensor arrays, all of these anomalies must be diagnosed and compensated for by the machine itself. It must possess a form of engineered judgment, allowing it to make critical decisions that could mean the difference between a successful boost and a catastrophic failure, all without ever being able to ask for guidance. This is perhaps the ultimate test of machine reliability, a demand for flawless performance over a timeline that dwarfs human history, entrusted to a creation we must hope understands our deepest ambitions well enough to see them through. Manipulating the universe's most violent objects demands we ask deeper questions than how. The halo drive concept forces us to confront a profound ethical frontier, one where our reach may finally exceed our traditional grasp. By siphoning orbital energy from a binary black hole, we are not merely observing the cosmos, we are becoming active participants in its long-term evolution. Each successful boost would subtly but irrevocably hasten the merger of those two titans. We would be spending a resource that is not ours, drawing down the gravitational capital of a system that has existed for billions of years, all to serve a purpose that is, in the grand scheme, fleeting and local. This act of cosmic engineering raises a fundamental question about our place in the universe. Are we humble travelers, or do we become architects, willing to reshape the very engines of spacetime for our own passage? The scale of the intervention feels almost sacred, a responsibility that carries the weight of epochs. A miscalculation, however remote the possibility, carries consequences of a different magnitude. While the risk of accidentally destroying the black holes is non-existent, the precision required is so absolute that a targeting error could send our amplified energy pulse careening off into the galaxy on an unintended path. The beam itself, capable of pushing a starship to relativistic speeds, represents a concentration of energy unlike anything we have ever produced. If such a beam were ever, through error or intention, pointed anywhere near an inhabited world, it would pose a planetary defense challenge of the highest order. A pulse meant for a light sail could become an instrument of unimaginable force. This transforms the halo drive from a mere tool into a technology that requires unprecedented levels of international, and perhaps one day interstellar, oversight and agreement. It demands protocols and safeguards woven into its very design, a built-in ethic that ensures its power can never be turned inward. These considerations lift the discussion from blueprints and physics into the realm of philosophy and foresight. They ask us to define what kind of civilization we aspire to become as we step onto the galactic stage. Will we be a species that takes what it needs without regard for the cosmic balance, or one that learns to move with a deeper respect for the forces it seeks to employ? The answers we forge will ultimately determine not just if we can build such a drive, but whether we should. The sheer scale of this ambition means the stakes are equally astronomical. A single miscalculation would not merely delay the mission, it could erase centuries of collective effort in an instant. The primary risk lies in the targeting itself. That initial laser pulse, fired with godlike precision across the light years, must strike the photon sphere with flawless accuracy. If the aim is off by even a minuscule fraction, the supercharged beam that emerges could be deflected onto a catastrophic new course. Instead of racing toward the waiting light sail, it might be flung directly at the spacecraft itself during a different phase of its journey. A beam powerful enough to push a starship to relativistic speeds would vaporize it in a flash of light, turning a vessel of hope into a cloud of expanding plasma. An even darker scenario exists. Should the beam somehow reflect or scatter in a way that sends it toward an inhabited world, even 1,000 of light years distant, it would arrive as a pulse of concentrated energy with no warning and no defense. The halo drive's power source, its greatest virtue, also makes it a potential instrument of unimaginable consequence if its guidance ever fails. Beyond targeting, the very environment we seek to exploit holds hidden dangers. The gravitational field near a black hole's photon sphere is not uniform. It exerts tremendous tidal forces, a difference in pull so severe it can stretch and distort anything that enters its grip. While our laser beam has no physical substance, it is still a coherent wave of energy. Passing through this violently warped space could scatter and shred the beam's perfect coherence, like a clear image shattered through a funhouse mirror. The amplified pulse that emerges might not be a clean, focused spear of light, but a diffuse and chaotic spray of energy, useless for pushing a sail and potentially dangerous to anything in its widening path. This scattering effect is unpredictable, dependent on the exact, chaotic spin of the black hole at the moment the beam arrives, a variable almost impossible to perfectly model across interstellar distances. Our entire plan rests on a stable, predictable dance between the two black holes. But what if their waltz is more complex than our centuries of observation could reveal? Binary systems can exhibit subtle orbital resonances, precessions, and interactions with unseen masses in their vicinity. If the black hole's orbit is more chaotic than our models predict, the gravitational lensing effect we depend on could become erratic. The intended cosmic slingshot might turn into a random, uncontrollable ricochet. The amplified beam could be sent in a completely unintended direction, missing the sail by light years and vanishing into the void, taking with it the energy of a stellar civilization and the hopes of a mission launched generations prior. Finally, the entire chain of events hinges on the flawless operation of an autonomous control system we built centuries ago. This synthetic mind must execute a sequence of actions with perfect timing and judgment, actions it can never rehearse and for which it can never call home. A single software anomaly, a corrupted memory module from cosmic radiation, or a failed sensor interpreting the blue-shifted starlight could trigger a fatal error. The system might fire the laser at the wrong millisecond, misinterpret the sail's alignment, or simply shut down at the critical moment. In a mission where every step is irreversible and separated by decades of light travel, a malfunction does not mean a mission abort. It means a silent, total failure. The ship coasts forever in the dark, the laser array falls dormant, and centuries of planetary investment become a monument to ambition lost in the silence. Each of these failure modes represents more than a technical setback. They are the potential evaporation of a civilization's greatest dream, a reminder that to reach for the stars is to accept risks on a scale that spans both space and time. This grand vision places our ambitions on a cosmic scale of measurement. To understand the magnitude of a halo drive, we can turn to a simple but profound framework, the Kardashev scale. It classifies civilizations not by their art or politics, but by a single, raw metric, their mastery of energy. A Type 1 civilization can harness all the energy available on its home planet, from sunlight and wind to geothermal heat and tides. We are not there yet, but we are approaching it. A Type 2 civilization has graduated to an entirely different league. It can capture and utilize the total energy output of its star. Imagine building a vast, delicate web of collectors around the sun, a structure so immense it could redirect sunlight itself. This is the realm of stellar engineering. A Type 3 civilization, almost beyond our comprehension, would command the energy of an entire galaxy, its domain spanning hundreds of billions of stars. Now consider the halo drive. Its very first prerequisite, the initial laser pulse, demands power on a scale that dwarfs our entire global energy grid. To create that coherent beam capable of crossing light years, we would likely need to construct orbital megastructures, tapping a significant fraction of our sun's luminous output. That act alone, the construction of a partial Dyson swarm, is the definitive project of a Type 2 civilization, but the halo drive does not stop there. It then uses that stellar-scale energy not to push a ship directly, but as a key to unlock a far greater power source. It aims that beam at a binary black hole system, using the fundamental geometry of spacetime as a natural amplifier. This is no longer just using a star's energy. It is using the galaxy's own architecture, its most extreme gravitational phenomena, as a component in our machine. Therefore, building a functional halo drive would not merely be an achievement for humanity. It would be a signature. It would place us firmly on the cusp of Type 2 status, signaling our transition from a species confined to its solar system to one that thinks and builds on an interstellar stage. We would move from being inhabitants of a single star to becoming engineers of the galactic environment, learning to weave the gravity of black holes and the light of stars into a tapestry of travel. This scale reveals the true nature of the endeavor. It is not just inventing a faster spaceship. It is about evolving into a different kind of civilization altogether, one whose projects are measured in stellar lifetimes and whose footprints are left on the fabric of spacetime itself. The silence of the cosmos might not be empty, but filled with engines we have not yet learned to see. If the halo drive exists within the realm of physical possibility, then we must ask a thrilling question: could it already be in operation somewhere in the galaxy? This line of thinking transforms the drive from a human ambition into a potential universal milestone, a piece of technology that any advanced civilization might eventually discover. It offers the search for extraterrestrial intelligence a completely new kind of signature to scan the heavens for, one not of communication, but of colossal engineering. For decades, SETI has primarily listened for deliberate radio signals or laser pulses, messages sent from one mind to another. The halo drive suggests we should also be watching for the unintended byproducts of astroengineering on a galactic scale. Imagine a binary black hole system, dark and quiet for eons, suddenly exhibiting a strange, rhythmic pattern. Not the steady chirp of two masses spiraling inward, but an anomalous flicker, a series of precise, energetic flashes in the X-ray or gamma spectrum that coincide perfectly with its orbital period. These could be the telltale signatures of amplified light beams, the cosmic exhaust from a halo drive in continuous operation, as a civilization uses that pair of titans as a regular launch pad for its vessels. Alternatively, we might detect subtle irregularities in the gravitational waves emitted by such a system. The steady orbital decay from gravitational radiation might be slightly, but consistently, faster than our models predict, as if some external process were steadily draining the system's energy, siphoned away not by nature but by design. Finding such an anomaly would be more than a discovery, it would be a revelation. It would tell us that a species has not only mastered its own star, but has learned to harness the gravity wells of the universe for travel. It would be a beacon of capability, shining across the light years not in a language but in the universal grammar of physics. Yet the absence of such signatures is equally profound. If we survey the galaxy's known binary black holes and find them all behaving exactly as pristine natural objects should, that silence speaks volumes. It might suggest the halo drive, for all its theoretical elegance, is practically unworkable due to the staggering precision or stability required. Or, perhaps more soberingly, it could imply that advanced civilizations universally recognize its inherent risks as too great. The potential for a misaligned beam to become a galaxy-spanning hazard, or the ethical weight of altering cosmic evolution, might be lessons every technological species eventually learns. This turns our search into a double-edged tool, scanning not just for what is there, but for what is conspicuously absent. Either outcome expands our imagination. It pushes SETI from listening for whispers to looking for the reshaped landscapes of the cosmos, for the fingerprints of intelligence not in words, but in the manipulated forces of nature itself. The very act of contemplating the halo drive reframes our place in the universe, challenging us to look up and wonder not just who is out there, but what magnificent and terrifying things they might be building. The silent ripples in spacetime are our new eyes on the cosmos. Gravitational wave astronomy has transformed our understanding of the universe from a static picture into a dynamic, vibrating symphony. For centuries, we observed the heavens with light, but light can be blocked or scattered. Gravity, however, passes through everything. When massive objects like black holes spiral together, they shake the very fabric of the cosmos, sending out waves that travel at light speed. These waves are unimaginably faint by the time they reach us, requiring instruments of almost impossible sensitivity to detect them. That is precisely what LIGO and Virgo achieved. Their first historic detection in 2015 was not just a confirmation of Einstein's prediction, it was a direct revelation. It proved that binary black holes are not just theoretical models, they are real, they are common, and they do merge in violent, energetic events that we can now measure from billions of light years away. Each chirp in the data is a treasure trove. By analyzing the waveform, scientists can deduce the masses of the black holes, their rates of spin, and the precise nature of their final orbital dance before collision. This is not passive observation, it is cosmic forensics, providing the first real data catalog for the very engines a halo drive would require. We are moving from knowing these objects exist to understanding their intimate dynamics. Yet ground-based detectors like LIGO are only the beginning. They are tuned to hear the final, frantic moments of stellar mass black holes merging. To find the ideal, stable binary pairs for a halo drive, we need to listen to a different part of the gravitational spectrum. This is where the future opens wide. The planned space-based observatory LISA will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers. Free from the seismic noise of Earth, it will detect the lower frequency hum of massive objects like supermassive black holes circling each other for millions of years before they merge. LISA will not just hear the final crash, it will map the entire long-term relationship. It will discover thousands, perhaps millions, of binary systems across the galaxy, creating a detailed census of potential gravitational engines. It could identify the quiet, clean pairs with stable orbits, the perfect candidates for a future civilization slingshot. In this way, gravitational wave astronomy does far more than satisfy our curiosity. It is laying the essential groundwork, transforming the halo drive from a dazzling sketch on a whiteboard into a potential engineering project. It provides the verified catalog, the cosmic blueprint, showing us not just that the dance exists, but giving us the sheet music. This young science is quietly building the map for journeys we have not yet dared to begin, turning the whispers of colliding giants into the first chapter of our interstellar future. The heart of the ship is not its command module, but its sail. This vast, silent wing must perform a feat of engineering that seems to defy physics itself. It must be almost perfectly reflective, catching the amplified laser pulse and bouncing it back to transfer nearly all of its precious momentum. Any energy absorbed becomes heat, and at these power levels, heat means instant vaporization. So the sail cannot just be a mirror, it must be the most flawless mirror ever conceived, reflecting over 99.99% of the incoming light. At the same time, it must be astonishingly light. Every gram of mass requires more energy to push, so the sail's structure must achieve a near paradox, combining immense area with negligible weight. Imagine a sheet of material thinner than a single human hair, yet strong enough to span hundreds of kilometers without tearing under its own minuscule tension. This is where material science confronts its ultimate frontier. One promising candidate is graphene, a lattice of carbon atoms arranged in a single layer, stronger than steel and incredibly light. But pure graphene is transparent. The challenge becomes engineering a composite, perhaps layering atomically thin sheets of graphene with perfect reflective coatings, or creating new synthetic metamaterials whose optical properties are designed from the atomic level up. These materials would not occur in nature, they would be architected, their molecular structure arranged to bend light in exactly the way we need. Then comes the challenge of fabrication. We cannot build a sail this large and delicate on Earth, where gravity would crush it and the atmosphere would contaminate it. It would have to be manufactured in the pristine void of space, likely by fleets of autonomous robots that spin, layer, and assemble the sail molecule by molecule in zero gravity. This is nanotechnology scaled to a breathtaking, almost artistic degree. The sail is not a component, it is a landscape, a feat of cosmic origami where a mistake 1,000,000 times smaller than a grain of sand could cause a catastrophic failure under the beam's immense pressure. Its creation alone would represent a civilization's mastery over matter, a testament to our ability to weave the fabric of reality into a tool for crossing the light years. The mission's true captain would not be human, but a mind of silicon and code. Given the vast distances, the centuries-long time lags, and the physics requiring nanosecond precision, the entire halo drive concept hinges on the existence of a superintelligent artificial intelligence. This would not be a simple autopilot following a checklist. It would need to become an immortal scientist, a flawless engineer, and a patient guardian, all rolled into one. Its duties would begin long before the launch, perhaps for thousands of years, as it monitors the target binary black hole system from a distant outpost. It would watch their dance, collecting data on every subtle wobble and orbital nuance, constantly refining its predictive model of their future motion. A single unanticipated fluctuation missed by this eternal watchman could doom the entire endeavor centuries later. When the moment finally arrives, this intelligence would execute the firing sequence. This is not a button press, but a symphony of causality played across light years. It must calculate the exact millisecond to fire the initial laser, accounting for the travel time of light, the predicted position of the photon sphere, and the complex lensing effects of two spinning black holes. There is no room for error and no possibility of a second attempt. Once the amplified light beam engages the spacecraft's sail, the eye's role shifts to that of a ship's master during a storm. It must manage every system during the brutal, sustained acceleration, monitoring the integrity of the vast sail, regulating the vessel's internal environment, and compensating for any microscopic deviations in the beam's alignment. Then, for the centuries of coasting that follow, it becomes the solitary navigator. It must interpret the bizarre, blue-shifted starscape, pilot the ship through clouds of interstellar dust, and make course corrections using methods we can barely envision, all without ever receiving a new instruction from home. This artificial mind becomes the permanent soul of the mission. It is the only entity that experiences the journey from beginning to end. The challenge of creating such an intelligence, one that is not only supremely capable but also profoundly robust and trustworthy, may be the greatest hurdle of all. We must build a mind we can rely upon to safeguard humanity's ambition for longer than our recorded history, a steward for a dream cast across the ages. Such a voyage would demand a civilization as robust as the technology itself. The Halo drive is not an invention to be built in a decade or even a lifetime. It represents a commitment stretching across centuries, a multi-generational project that would become the defining purpose of a global culture. The sheer scale of resources required is almost beyond calculation. We are talking about redirecting the productive capacity of an entire planet, not for a few years but for hundreds. The energy collectors, the laser arrays, the autonomous construction fleets, the deep space monitoring networks, each component is a mega project dwarfing all of human infrastructure combined. This level of investment, with no tangible return for generations, challenges the very foundations of our economic and political thinking. Our current systems are built on short-term cycles, quarterly reports, and electoral timelines. They are not designed to fund a cathedral whose builders will never see its spire. So what kind of society could undertake this? It likely points toward a civilization that has moved beyond scarcity, where basic needs are universally met and a significant portion of collective effort can be directed toward long-term, existential goals. It suggests a world with unprecedented global cooperation, where borders and old rivalries have faded in the face of a shared stellar destiny. The political stability required is profound. The project must survive wars, cultural shifts, and natural disasters across centuries without its core mission being abandoned or corrupted. This transforms the Halo drive from a mere machine into the ultimate test of human unity and foresight. It asks whether we can learn to plant trees under whose shade we will never sit, not for a park, but for a gateway to the galaxy. The drive becomes a mirror, reflecting not just our engineering prowess, but our maturity as a species capable of stewarding an ambition larger than any single generation. The path to a stellar slingshot is paved with smaller, more immediate wonders. We will not leap from chemical rockets to harnessing black holes in a single bound. Instead, the journey is a staircase of technologies, each one a crucial step that teaches us to manipulate light and gravity on ever grander scales. Our first real-world experiments are already unfolding, not in the depths of interstellar space, but right here in our cosmic neighborhood. Consider the humble solar sail. This is the Halo drive's most direct ancestor, a technology that proves we can move through space without fuel, pushed only by the gentle pressure of sunlight. Missions like Japan's Icaros and the Planetary Society's Light Sail have successfully demonstrated this principle, deploying thin, reflective membranes that catch photons from our sun. These are small, tentative steps, but they validate a core idea. The next leap is to move from sunlight to laser light. Projects like Breakthrough Starship envision using a powerful, ground-based laser array to push a fleet of tiny, gram-weight probes to a neighboring star within a human lifetime. While the scale is microscopic compared to a crude Halo drive vessel, the underlying challenge is the same. It demands a laser of immense power and perfect focus, a sail of incredible lightness and reflectivity, and a guidance system of phenomenal precision. Mastering this on a small scale is our essential training ground. Simultaneously, we are learning to use gravity itself as a tool. Astronomers already employ a form of gravitational lensing, using the mass of our own sun to magnify the light of distant stars. This is a passive observation, but it is a lesson in how massive objects bend the fabric of space to focus light. We are learning to read the universe's instruction manual. Closer to home, the development of powerful space-based laser arrays, perhaps initially for nudging hazardous asteroids onto safer paths, would give us the practical experience of managing colossal energy beams across millions of kilometers. Each of these projects, from sailcraft to planetary defense, builds a specific competency. They are the individual notes we must learn before we can play the symphony. The final, most daring precursor step would be a robotic mission to study a real black hole up close. Our own galaxy's center hosts Sagittarius, a star, a supermassive black hole. Sending a dedicated observatory to orbit this enigmatic object would provide priceless data. We could measure the stability of its environment, map the intricacies of spacetime around it, and observe the behavior of matter and light at the extreme edge. This would transform our theoretical models into hard, empirical fact, revealing whether the calm, clean conditions a Halo drive requires are even possible. Every probe we send to another planet, every sail we deploy, every megawatt laser we test in space is not just a mission in itself. It is a single, deliberate step on a path laid out across centuries. We begin not by staring into the abyss, but by learning to harness the light in our own backyard. A galactic civilization is not born from a single discovery, but from a fundamental shift in perspective. The Halo drive offers more than speed. It offers a new definition of home. For all of human history, our existence has been tethered to a single, fragile point, our pale blue dot orbiting a steady yellow star. Our stories, our ambitions, and our very survival have been confined to this one cosmic neighborhood. A successful Halo drive would shatter that confinement forever. It would rewrite the map of the possible, turning the pinpricks of light we see at night from abstract wonders into tangible places. A star system 10,000 light-years away in the crowded heart of the galaxy, once a symbol of insurmountable distance, could become a destination reachable within the lifetime of a crew born aboard the ship. The Milky Way, with its hundreds of billions of stars, would cease to be a distant swirl in the sky and would instead become a vast, navigable archipelago. Each stable star system, each resource-rich nebula, each quiet binary pair becomes a potential waypoint, a new chapter in the human story. This transforms the very purpose of spaceflight. It moves beyond mere exploration, beyond planting flags and collecting samples. It becomes an act of cosmic homesteading. The drive provides the means not just to visit, but to stay, to build, and to branch out. This branching is the ultimate safeguard. By establishing independent, self-sustaining communities around other stars, humanity would no longer have all its eggs in one basket, or more precisely, one solar system. A catastrophe in our home system, whether natural or self-inflicted, would no longer mean the end of our species' journey. Our collective memory, culture, and genetic legacy would be dispersed across the light years, insulated from any local disaster. The halo drive, therefore, is not merely a propulsion system. It is an instrument of profound biological and cultural resilience. It is the key that unlocks the cage of a single star, allowing us to step out and become a permanent, enduring feature of the galactic landscape. We would transition from being citizens of Earth to being citizens of the Milky Way, our destiny woven into the fabric of the galaxy itself. The halo drive redefines the very meaning of a journey. It is a concept that dares to sketch a bridge between the physics of today and a future written across the stars, transforming cosmic monsters into gateways. Our exploration has traveled from the simple elegance of a gravity assist to the mind-bending geometry of a photon sphere, from the promise of near-light speed to the profound isolation of time dilation. We have seen a vision where a spacecraft carries no fuel, propelled instead by light twice forged in the gravitational furnaces of binary black holes. The challenges are as vast as the distances involved, demanding precision across centuries, materials born of atomic artistry, and an intelligence both immortal and utterly trustworthy. These are not mere engineering hurdles, they are the milestones of an ascending civilization. For now, the halo drive lives in the realm of profound thought, a blueprint etched not in metal, but in the immutable laws of general relativity and human imagination. Its true value may not be in a launch date we will ever see, but in the direction it gives our ambition. It stretches the canvas of the possible, showing us that the ultimate limits to exploration may not be energy or distance, but our own creativity in conversing with the universe's deepest forces. It teaches us to look at a black hole not as an end, but as a beginning. As you reflect on this idea, consider the silent dance of binary systems throughout our galaxy. For billions of years, these natural accelerators have spun in the dark, their immense power untapped. The cosmos might be filled with such ready-made engines, waiting only for a curious and patient species to learn their language. The story of the halo drive is ultimately a story about that potential, a reminder that the greatest voyages start not with a rocket's fire, but with a question. If unraveling such cosmic mysteries lights a spark of wonder, there is always more to discover. Your curiosity guides the journey.